Are we alone in the universe? It's arguably one of the greatest mysteries in human history. Welcome, everyone. Today, we're diving into a massive explainer all about the search for extraterrestrial life. We're going to travel from the ancient, dusty riverbeds of our neighboring planets all the way out to distant, ocean-covered worlds literally light years away. I am so incredibly excited to guide you through this, because we're not just dealing in science fiction here. We're going to look at the exact frameworks and the cutting-edge observations that scientists are using right now to hunt for life.
It really all boils down to this single, profound question. If the exact right conditions for life came together here on our home planet, could that same cosmic recipe have been cooked up somewhere else in the vast, sprawling universe? To figure that out, we're going to take a sort of inside-out journey. We'll start with the fundamental ground rules of biology, travel through our own local solar system, and then cast our gaze deep, deep into space.
Okay, let's jump right in with Act 1, the blueprint of life. Before we can even begin searching the stars, we have to establish what it is we're actually looking for. What makes a world capable of hosting biology in the first place?
Naturally, our starting point has to be Earth. But astrobiologists don't just look at our planet as some static, unchanging rock. They use this super fascinating concept called dynamic habitability. It's basically the idea that a planet's environment and its potential for life co-evolve together over time. Habitability is a continuum, you know? A planet's interior, its magnetic field, its atmosphere, and its life forms are constantly interacting. So to find life out there, we have to look for worlds that can maintain that kind of dynamic balance over long geological timescales.
So, what are the absolute must-haves? Well, based on our sample size of exactly one inhabited world, we need 3 fundamental ingredients. First, liquid water. Second, the right chemistry, specifically organic compounds and essential elements we call CNOPs. That's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And third, you need an energy source to actually sustain cellular metabolism. These 3 pillars form the absolute ground rules for our cosmic detective work. If a world has these, it is officially on our radar.
Moving right along to Act 2, the local search. Let's take that rulebook and apply it to the actual playing field, our immediate planetary neighbors. This is where we have the incredible luxury of sending physical robotic missions to hunt for clues.
We have to start with Mars. Now, I know Mars might seem like a harsh, frozen desert today, but billions of years ago, it actually had widespread bodies of liquid water and mild surface temperatures. And this brilliantly illustrates why Mars is just so vital to scientists. It has a complete, fully intact, 4-billion-year-old geological record sitting right there on its surface. Honestly, Earth doesn't even have a preserved record that old. This makes Mars the perfect, pristine canvas for our rovers to search for the chemical or physical fingerprints of ancient past life.
But wait, the habitable zone in our solar system extends way further out than Mars. Let's talk about the mind-blowing ocean worlds orbiting our giant gas planets. It's almost a tale of 2 extremes. On one hand, you have Europa at Jupiter and Enceladus at Saturn. These moons harbor massive subsurface liquid water oceans. They're kept warm by tidal heating, and they have chemical salts and energy sources interacting with a rocky seafloor. On the other hand, there's Saturn's moon Titan, which is totally unique. It has a subsurface water ocean too, but on its surface, it has literal lakes and seas of liquid hydrocarbons and natural gas, all shrouded by a thick nitrogen and methane atmosphere. The sheer diversity of potentially habitable environments right in our own backyard is just staggering.
And this isn't just theoretical guesswork. NASA's upcoming Europa Clipper mission is launching to directly investigate Europa, a moon that scientists believe has held onto its ocean for 4 billion years. That is more than enough time for the ingredients of life to start mixing. What's even more mind-blowing is that this single moon potentially holds twice as much liquid water as all of Earth's oceans combined. Think about that for a second.
Next up, Act 3, Distant Echoes. Having explored our local neighborhood, we're now turning our gaze outward. As we move to distant exoplanets orbiting completely different stars, our tools have to evolve from robotic spacecraft to incredibly powerful telescopes.
When you're peering across light years of space, you're looking for what scientists call a biosignature. Basically, it's an observable chemical byproduct or even a surface reflection that is created by life. But here is the massive scientific hurdle. If we spot a gas like methane in a distant atmosphere, we have to definitively prove it was produced by a living metabolism. We have to completely rule out all normal planetary chemistry, like volcanoes or standard photochemistry. It's an incredibly strict standard of proof.
So how do we actually pull this off?
Scientists use a brilliant framework called atmospheric retrieval. Step 1. Space telescopes, like the James Webb, capture the spectrum of light passing directly through an exoplanet's atmosphere. Step 2. They analyze that light to model the planet's atmospheric chemistry. But step 3 is where the magic happens. They don't just look at how much gas is there, they use physics to infer the actual surface gas fluxes. Basically, they want to see if the planet is constantly pumping out gases at a rate that only a biological metabolism could possibly sustain.
Which brings us to Act 4, the ultimate question. We've talked extensively about the search for simple, microscopic biology. But what about intelligent life? This brings us to the absolute most suspenseful part of our explainer.
If an exoplanet actually hosts an advanced civilization, we might be able to detect a technosignature, a giant flashing observable indicator of advanced technology. And one of the best possible beacons we could look for is a persistent narrowband radio signal. Why? Because nature doesn't easily create signals under 500 Hz on its own. But human technology? We do it all the time with our radar and our deep space networks.
Enter K2-18b. This world is absolutely fascinating. It's a sub-Neptune exoplanet sitting right smack in the habitable zone of its host star. The James Webb Space Telescope recently detected methane and carbon dioxide in its atmosphere. Because of this, scientists think K2-18b might just be a Hycean world, a planet with a thick, hydrogen-rich atmosphere blanketing deep, stable oceans. Since it's such a prime candidate for habitability, scientists decided it was the absolute perfect target for a dedicated technosignature hunt.
Here is exactly how they did it. Astronomers aimed 2 powerhouse radio observatories right at it, the Very Large Array in New Mexico and the Meerkat telescope in South Africa. They listened across a massive range of frequencies, from 544 MHz all the way up to 9.8 GHz, across multiple different timeframes. And to make sure they weren't just accidentally hearing our own earthly radio interference, they specifically looked for signals exhibiting a predictable Doppler drift, one that matched the precise orbital mechanics of the K2-18 planetary system.
Now get a load of the sheer magnitude of this number, 10 to the 12th to 10 to the 13th watts. That was the detection limit of this massive radio search. To put that staggering, mind-bending figure into perspective, they were basically listening for isotropic narrowband transmitters operating at the scale of massive, civilization-level planetary radar systems. Now let me be super clear here, just so we strictly separate scientific fact from speculation. The search found absolutely no signals consistent with an artificial or extraterrestrial origin. No aliens have been discovered yet. But honestly, this non-detection is actually a massive victory for science. It proves that our multi-telescope, multi-epoch interferometric framework works flawlessly. We now have the exact methodology needed to search nearby, potentially habitable exoplanets moving forward. Which leaves us with this one final thrilling thought. We know for a fact the ingredients for life are abundant. We have ancient riverbeds on Mars, hidden oceans on Europa, and Hycean worlds orbiting distant stars. Our tools for detecting biosignatures and technosignatures have literally never been more powerful. So, if the stage is already set across the vastness of space, when will we finally read the right signature in the stars? Thank you so much for joining me on this incredible explainer, and remember, keep your eyes looking up.